I'm going to go into Fischer projections. Fischer projections are very important in biochemistry. They're commonly used there. We use them all over organic chemistry also. In your book, this may be later in the chapter than the chapter that chirality is covered in, and that's okay. I'm covering it now because if someone takes the first organic chemistry, they're allowed to go ahead and take a biochemistry course. And in biochemistry, they use Fischer projections shown down here. And so I want whoever takes a first chemistry to be ready for biochemistry, since the first chemistry is the only prerequisite for biochem. Fischer projections are a shorthand for showing chiral compounds. We're already used to looking at two lines intersecting and thinking there's a carbon right here. So this actually looks like this molecule. You can see this carbon. There's a hydrogen hydroxyl group attached, and then there's an aldehyde group and a methyl hydroxy group. So we can see that's the same compound. How is it that this is portraying this? Well, what we do is to change this to a Fischer projection, I rotate this compound so that the methyl hydroxy group actually comes down and this hydroxyl group goes up here to the side. Let me show you. Okay, it is the same thing as this. You see how the hydrogen is sticking out at you and the hydroxyl group is coming out at you, but this aldehyde group and the methyl hydroxy group are going back. It is as if these two are arms coming out to hug you, and this are leaning back away from you. And so always remember, when you're looking at the Fischer projection, the things that go right to left are coming out at you, and the things that are going up and down are going back. How is this R-glyceraldehyde? Well, let's assign the chirality. The hydrogen is the lowest possible priority, so it's to the back. This is the highest possible priority group. This is next highest, and then we have this group as being lowest. So the rotation is clockwise, so it's R. We can assign that here on this group also by looking at this is the lowest priority group, highest, second highest, and next priority. And if I look at this, hydrogen's coming out. If I assign priorities, I see my priorities go counterclockwise. All we have to do is say the hydrogen's coming out. I have to flip my rotation, so this is actually R. This right here is representing this. Whenever we look at a Fischer projection, the right and left are coming out at you, and the up and down are going back. So I can imagine this when I'm looking at this and be able to assign priorities and then rotation. The thing about Fischer projections is that we can rotate them 180 degrees, and it doesn't change the structure, because if I rotate this 180 degrees, this is still side to side, and this is still back and back. All I've done is rotated the molecule around. However, if I do a 90-degree rotation, what I find is you actually change the chirality of the compound. You change it from S to R. So when I take this and I rotate the entire structure, 90 degrees. So the hydroxyl group goes down here. This goes over here. This goes over here, and this goes up to the top. When I do that, it changes this to the enantiomer. So sometimes that's a useful thing to know. It's very hard to look at this and be able to tell they're enantiomers without assigning them. So being able to just rotate it around by 90 degrees, you would know that it's an enantiomer. If you rotate by 180 degrees, what you find, See, this is rotating by 180 degrees. The hydrogen goes dunk dunk, okay, to here. The hydroxyl group goes dunk dunk to here. The aldehyde goes boom boom to the top, and the methyl hydroxy group goes boom boom to the bottom. This and this are the same structure. They just have been flipped in space. Fischer projections can have 3 groups rotated while the other is held in place, and you don't change the chirality of it, the specific rotation. So if I look at, I'm going to hold this group in place, and I'm going to rotate these 3 groups. So the hydrogen goes 1, 2. The hydroxyl group goes 1, 2. And the methyl hydroxyl group goes 1, 2. I get this compound, which is the same thing. And you can go ahead and assign specific configuration and specific configuration, and what you'll find, these are both R. If I go and I look over here at this one, I'm rotating again 1, 2. I'm taking this 1, 2. I'm taking this hydrogen 1, 2, and I'm taking this methyl hydroxide 1, 2. This is the same thing as this. So rotating it by 3 groups around and around and around does not change anything. It's basically like the rotation that you would find of rotating around a single bond right here. No change. One way, the way that I do Fischer projection assignments is, you saw that I just assume the lowest priority group. I look at it and I look to see is it forward or back, and assign the priority of the others. And then if it's forward, I know I have to flip the assignment from R to S or S to R. If it's back, then you go ahead and use it. If you want to, you can use this method. I'm not going to go through it, but this is another way that people use. Use whatever works for you. Okay, let's look at these molecules, and we're going to assign chirality to each of these molecules. What I'd like you to do is start with this molecule. Hold on, let me point to it. Start with this molecule and assign specific rotation using whatever method works for you. Okay, what I'm going to do is I'm going to look at this carbon first. This is the highest priority group. This group down here would be the second highest, and then the methyl would be last. And the hydrogen, of course, is the one that we would put behind. We see that the hydrogen is coming out at you. If I assign rotation, this is clockwise. So the hydrogen's coming out, so it must be counterclockwise and S. If I look at this one, I'll do the same thing. Highest priority, second highest priority, and then methyl is third. The hydrogen's coming out at you, so this was clockwise, so it must be an S. If I look at this compound, highest priority, second highest priority, and then the methyl group. This is clockwise rotation. The hydrogen is coming at you, so it's S. This is highest priority, second highest priority, then the methyl group. That's counterclockwise rotation. The hydrogen's coming out instead of going back, so it's R. If I go down here and look, this carbon has 2 groups the same, so it's not chiral. Only this carbon is chiral. I assign priorities number 1, number 2, and then number 3. The hydrogen is coming out at you. That was clockwise, so it must be S, reversed, because the hydrogen's coming at you. If I look at this one, the hydrogen is coming out at you. Highest priority, second highest priority, then the carbon. So it is going to be S. Highest priority, next, highest priority. This is higher priority than this one because there's only one bromine here and there's two bromines here. Highest priority, second highest priority, third, that's clockwise, but the hydrogen's coming out, so it's S. Go ahead and look at these two and figure out, are these enantiomers, diastereomers, methyl compounds? What is it that we have here? What's the relationship? Okay, so if I look at this, the hydrogen's going back. Highest priority, bromine, then ethyl, then methyl. That's clockwise, so that must be R, because the hydrogen's going back. This hydrogen's coming out. If I assign rotation, it would go clockwise. It's going to be S, because the hydrogen's coming out. So this is R, and this is S, so they are enantiomers. Another way that you can do it is to go ahead and see that to interconvert this structure and this structure, I have to flip two groups. When you flip two groups, you get an enantiomer. All right, so now what we're going to do here is determine the relationship between these two compounds. Okay, I'm going to look at these two. On both of these carbons, the hydrogens are coming out. So I assign priorities. 1, 2, 3. That's clockwise, hydrogen out, so it's S. This one is 1, 2, 3, counterclockwise, hydrogen out, R. If I look over here, this one is 1, 2, 3, hydrogen out, clockwise rotation, so this is S. If I look at this one, 1, 2, 3, clockwise rotation, hydrogen out, so it's S. So the assignments are S, R, and over here, S, S. These two are diastereomers. This one is actually a meso compound. Okay, which of these is S-bromochlorofluoromethane? They're all bromochlorofluoromethane. What you need to do is determine which one is S. So if I go ahead and look at this one, I can see the hydrogen. If I go ahead and put the hydrogen to the back, the lowest priority group, what I would have is bromine, chlorine, and then fluorine, and it would be clockwise rotation, so this is R. If I assign priorities here, I get bromine, chlorine, fluorine. The hydrogen, that's clockwise rotation, but the hydrogen's coming out, so this one's S. If I look at this one, the hydrogen's going back, so bromine, chlorine, fluorine, that's R. Here, the hydrogen is down. I assign rotation. Bromine is 1, chlorine 2, and then fluorine, and I would see that this is clockwise rotation, so this is R. The only one that is S is this one. Here is glucose. It's called ProS glucose, dextrose. This is a natural glucose that we have. Go ahead and look at this molecule and figure out how many possible diastereomers are there. This is kind of a hard problem, but it's going to teach you something interesting. Okay, if I look at this compound, I will see there is 1, 2, let me point to them. Okay, there is 1, 2, 3, and 4 chiral carbons. How many possible combinations do you have? Well, what we find is with 4 chiral centers, we have 2 to the 4 possible stereoisomers. 2 to the 4th power, that's 2 times 2 times 2 times 2, that gives me 16. Okay, 4 times 4 is 16. 16 possible stereoisomers. One of them is glucose, positive glucose, what we call positive glucose. The other is going to be its enantiomer. All of the rest of them are going to be diastereomers. So how many diastereomers do you have of glucose? You actually will have 14. Why did I want to do this problem with you? Because it's so hard. That's a really hard one. The reason I wanted to is I wanted to give you this formula that the number of stereoisomers that you have for any molecule is you count up how many chiral carbons you have, or chiral centers, and then you're going to have 2 to that many carbons stereoisomers. It's a very useful little formula. Okay, so go ahead and analyze these compounds and figure out which one of these is R2-bromobutane. Okay, if I look at this compound, this is 2-bromobutane, but there's no stereochemistry shown. So I can't say that it's R or S. It's undefined. It could be either of those. When we do this, we're usually not concerned about the chirality of the compound. If I look at this one, it specifies the chirality. The hydrogen's coming out. The priorities go bromine, ethyl, methyl. That is counterclockwise with the hydrogen out. This one is R. If I look at this, the hydrogen's back. Bromine, ethyl, methyl, that's counterclockwise, so this one's S. If I look at this one, the hydrogen is coming out. Bromine, ethyl, methyl, that's clockwise rotation, but with the hydrogen out, that's an S compound. The only one that is R is this one. Okay, reactions. Achiral reagents lead to either achiral products or a race mate with when you have a chiral compound react with them. So a chiral compound will either lose its chirality with an achiral reagent or we get a race mate. And remember, a race mate is a 50-50 mixture of 2 enantiomers. Chiral reagents will lead to a chiral product if, in the process of forming the product, you don't have a position that the compound gets to that is symmetrical. Not a big deal here. I'm not going to test you on that one. This one I may test you on. Chiral centers are going to be unchanged by a reaction that is not at the center unless one of the groups is modified so that it is the same as another group. And we're going to go through examples of these. Every time you have a reaction, you have to analyze the situation and say exactly what's happening here. Do I get a chiral product? Do I get racemization? What's going to be happening? And you have to kind of understand the mechanism. We don't have many mechanisms yet. We don't have any to speak of. And so you have to think through your reaction and your reagent. Here's an example. I can take this compound and it is achiral. When I react with hydrogen bromide, I get 2 compounds that come out. One is S and the other one is R. So this is S and this is R. So if I look, it would be a 50-50 mixture that results from this. So a race mate results. If I look at this reaction, what happens here is the potassium hydroxide pulls the hydrobromic acid off and puts a double bond in here. this carbon was chiral ahead of time, but afterwards this carbon's in a double bond. So the chiral compound becomes achiral. Right now, we're not going to be doing many reactions. In this chapter, we don't do any reactions. Later, we're going to be looking at reactions in chirality, and that's when I'll be testing you on this. At present, we're going to have to just ignore reactions. But in the subsequent chapters, we're going to have reactions. And before we have this test, we're going to revisit all this. There's two other types of things I want to talk to you about, and that's prochirality. Prochirality can come about through two things, either phases of a compound or through the reaction of one group of the same, making something different. So that's what we're talking about, because I know right now you're confused. Prochirality basically says a compound can react, become chiral. And when we look at a compound like this, you can see there are double bonds, so it is not chiral. However, if a chiral compound reacts with this, what we find is it will react differently with this side than with this side. And so we actually have faces to the compounds that we assign, so that if we ever do react it with a chiral compound, we can refer to one face or the other, and the selectivity might be discussed. So it's a way of actually discussing reactions and what might happen. So what we do to look at a compound like this and say what face do we have is we realize we can have it flipped. Either it can go flat and have the hydrogen on the right, or it can go flat and have the hydrogen on the left. It's the same compound either way, but one side is different from the other for a chiral compound. Okay, so if I go ahead and I look at the possible faces, what I do is I put it on one face and assign priority to the groups. So the oxygen would be highest, methyl next, and then the hydrogen. If I flip this over so the hydrogen is on the right, the rotation would be counterclockwise, and I call it psi. If I flip this so the hydrogen goes to the left and the methyl to the right, what I would find is I'm looking at a face where oxygen, then methyl, then hydrogen, that's clockwise rotation, and I call that face ray. So this side is the psi, and the other side is the ray face. So go ahead and look at these molecules, how they're put on the page, and say, is the face that's up ray or psi? And so what I mean is the face that's up, the face you're looking at as you look down on these molecules. Okay, let's go ahead and look at this molecule. You see oxygen, ethyl, methyl. The rotation is clockwise, so it's ray. This one's nitrogen, methyl, hydrogen. The rotation is counterclockwise, so this is the psi face. If I look at this, hydrogen is lowest priority. This side is highest priority. The rotation on this carbon is that's clockwise. So this is ray for this one, psi for this one. But the entire molecule is symmetrical, so there's no ray or psi face because one side is identical to the other. So ray, psi, ray, but there's no face on this molecule, so the entire molecule. Okay, what we're going to do is we're going to look at a molecule that is not chiral, that has an achiral carbon, but it could become chiral by changing one of the groups. This is called a prochiral molecule. So we're going to, or a prochiral carbon. So this is another type of prochirality. So let's look at this molecule. If an enzyme were to grab this molecule, so it grabs this by one group and grabs this by another group, and then the rest of the enzyme wraps around and modifies one of these hydrogens, it would only modify either the right or the left. And the reason is that enzymes are chiral, very, very chiral. They have many chiral carbons. And so once it grabs those two groups, this hydrogen would be different to it than this one. So let's say the enzyme goes and modifies this group. That would be a different molecule, the enantiomer, as if it grabbed this hydrogen and modified it. Although this molecule is planar and achiral, when the enzyme interacts with it, this hydrogen is going to be different from this one. So now what we're going to do is we're going to identify the hydrogens as being ProR or ProS. And so we can actually discuss which one would react. How do we do this is we take a same group, the hydrogen is the same as this hydrogen, and we're going to look at this and we're going to say we do something to this to change it. So hydrogen is the lowest possible priority. The only way to change it would be to make it a higher priority group. So just assume we change hydrogen to deuterium here. If I do that, this hydrogen is a lower priority then, and I can assign a rotation to this molecule, highest priority, next highest priority, and then this one. The hydrogen's coming out, that's clockwise rotation, so this would be an S compound if this was modified. So we say this hydrogen is ProS. If this one's ProS, this one will be ProR. So I can go through changing the priority on this one. If I change the priority of this one so it's slightly higher, this is highest, that second, and this is back to the other. So it would be 1, 2, this would be held back, 1, 2, 3. The rotation on that is counterclockwise, but the hydrogen's coming out, so it would be R. So this hydrogen is called ProR. Okay, so for each of the identified hydrogens that we have here, what I want you to do is identify, is this ProR or ProS? Is this ProR or ProS? Is this methyl ProR or ProS? So go ahead and figure this out, and then we will, I'll start going through it with you after you restart the lecture. So if I look at this group, I can see that if I change this to a deuterium, the hydrogen would be back. This would be highest priority, second, and then the hydrogen. If I look at this, that is counterclockwise rotation, the hydrogen is out, so the molecule would then be R. So this is ProR. If I look at this molecule, I will see that this hydrogen is the same as this, but this methyl is the same as this. So this hydrogen, even if I change the priority of it, it's not going to be a chiral molecule. So it's neither ProR or ProS. If I look at these two groups, I will see those two are different. So let's go ahead and change the priority of this. If I change the priority of this so it's slightly higher than this, the hydrogen is back. It's forward. So it would be number 1 priority, number 2, and then number 3. That is counterclockwise rotation. The hydrogen's coming out, so that this methyl group would therefore be ProR. So ProR, neither, and then ProR.